right? So last week in the lecture we started to look at basically ke there are certain types of motion where bodies cannot be treated like particles, और उसी वजह से we had started to look at के okay, but in real world we are actually going to be interested primarily in the motion of bodies. So इसलिए perhaps we now need to look at rigid body motion. तो इसके अंदर we started to describe कि हम एक बड़ा narrow subset of the motion of bodies देखेंगे, which will be first of all that it will be planar. That means that the motion will be occurring just in 2D, just in one plane. Secondly, for this course we will only be looking at rigid bodies, which means that there will be no deformation in those bodies. So last time we started to look at the two first types of rigid body motion, which was translation and rotation about a fixed axis. And then the third one, which was the general plane motion, that is when you have translation and rotation both occurring at the same time. That one we're going to do later on. So abhi bhi we're still continuing on with our translation and rotation. So just as a little recap of translation, we saw that in translation, that is the case when all of the points of the body या फिर all of the particles of the body have the same velocity and acceleration, such that what we can do is we can choose just one point and represent the body of the body of the motion, apologies, the motion of the body using just the motion of that one point. So normally what we tend to do is that we just choose the center of mass and we represent the motion of the entire body using the motion of the center of mass. Why? Because under translation, then all of the particles have the same velocity and acceleration. Right. So this was the case when we have rigid body translation. This was the case when the rigid body behaves like a particle. ठीक है जी. So everything that we've been doing thus far were examples of exactly this. ठीक है जी. Also note that translation within it contains rectilinear or curvilinear translation. If somebody does not recall what they were, please go take a look at the slides. जिसके अंदर example given है कि what is rectilinear translation and what is curvilinear translation. Okay, perfect. Then last time as well we'd started to move on to look at rotation, and this was the new part that we were doing. So how far we had gotten last time was that we had just considered looking at only the rotatory part of the motion of the body, and we saw how कि अगर हम एक axis के about वो body rotate कर रही है, then we can use the right hand grip rule to figure out कि उस rotation का vector direction क्या है और उसकी rotatory direction क्या है, right? So remembering if I go to home, I think ये 1 2 3 disappear हो जाएंगे. Yes. So remembering कि if we take our right hand and we point the thumb in the direction of the axis, that is we point the thumb in the vector direction, then the curl of our fingers gives the direction of the rotation. Perfect. So using this right hand grip rule, then we saw that if something was curling in this anti-clockwise direction, so to speak, when we're looking at it from above, then that means that the vector direction must be upwards. Okay. Or इसी से we had started to define angular displacement, angular या फिर angular position, angular velocity and angular acceleration. और इसकी हमने यही डेफिनेशंस देखी थी कि यूजिंग अ रेफरेंस लाइन के कोई मे बी परहैप्स जो इनिशियल पोजीशन थी ऑफ द बॉडी उस पर हमने कोई लाइन बना लें, देन एज द बॉडी रोटेट्स इट्स गोइंग टू रोटेट रिलेटिव टू दिस रेफरेंस लाइन, राइट. सो उसकी वो जो चेंज इन पोजीशन हो रही है एज इट्स रोटेटिंग, then that change in position can be referred to as the change in its angular position, and that is of course represented as this d theta. अगर theta को हम position से represent कर रहे हैं, position को theta से represent कर रहे हैं. Perfect. Then of course our angular velocity, as the name implies, is the rate of change of this angular position. So it's thus this d theta by dt, rate of change of angular position, and it is represented by omega. तो इसलिए इसको एंगुलर वेलोसिटी कहते हैं। और इसी के बाद फिर द सेम एज जो हम रेक्टिलिनियर मोशन में कर रहे थे उसी तरह फिर एक एंगुलर एक्सेलरेशन भी हम डिफाइन कर सकते हैं, विच इज़ द रेट ऑफ चेंज ऑफ दिस एंगुलर वेलोसिटी। सो मतलब ये कि डी ओमेगा बाय डी टी जो है वो हमारी एंगुलर एक्सेलरेशन हो गई। Perfect. So when we had defined all of these things, we started to notice कि oh, ये तो angular position, angular velocity और angular acceleration की जो expressions है, they look extremely similar to the expressions we had for just rectilinear position, velocity and acceleration. तो इसीलिए वो जो किनेमैटिक इक्वेशंस हमने सबसे शुरू में इन द आई थिंक इन द सेकंड लेक्चर वी डिराइव्ड, वी सॉ कि इफ़ दीज एक्सप्रेशंस आर completely equivalent for that rectilinear case, then those same kinematic relationships apply here as well, such that if we integrate these three kinematic equations for the case when we have constant angular acceleration, then हमारे पास वही expressions आ जाती हैं जो हमारे पास रेक्टिलिनियर ट्रांसलेशन के लिए थी फॉर ए पार्टिकल। परफेक्ट। द ओनली डिफरेंस बीइंग कि अब एक्चुअली ये रोटेशन के लिए हो रहा है, बट जस्ट बिकॉज वो इक्वेशंस वर एनालगस, उनकी सेम फॉर्म थी, इसलिए वी वर एबल टू डू दिस। Okay, right. So this was all very nice and useful because we had been looking at the entire body and we'd been looking at how there would be changes in its position d theta, and there would be a change in its it would have an angular velocity and an angular acceleration. But now what I want to point out to you is why I separated these guys out. Why I separated out of course my touchpad. Why I separated out d theta, alpha and omega is because I want you guys to notice that as this entire body rotates about this axis, तो जब वो रोटेट करेगी तो अगर मैं इस पॉइंट P को देखूं और वो अगर इस d थीटा से मूव करे, और फिर मैं अगर एक और पॉइंट में भी Q को देखूं, और एक्चुअली Q does not need to be on the surface, Q could be here. तो Q के साथ क्या होता है? Q की अगर इनिशियल पोजीशन ये थी और अब वो आगे की तरफ मूव कर गया है, समथिंग लाइक दिस, तो व्हाट डू यू थिंक उसका चेंज इन एंगुलर पोजीशन क्या होगी? वो भी d थीटा होगी। Why? Because this is a rigid body. So however much P rotates by, Q would also rotate by that same degree or same radian, right? So this d theta is the same for all of the particles on the body. Next, इसी वजह से I had also considered the angular velocity and the angular acceleration first of all, because as I've just discussed for the angular position, the change in angular position, for all particles on the body, they have the same angular velocity and the same angular acceleration. That is, उन सब का d theta same होता है, उन सब का theta dot same होता है, and उन सब का theta double dot भी same होता है। d theta तो हमारी angular position का change हो गया, theta dot of course is omega, rate of change of d theta, and theta double dot is alpha. So these are terms, the theta dot and theta double dot are terms that you guys have already seen when we were looking at the curvilinear motion of a particle in polar coordinates. But the only reason why this omega symbol and this alpha symbol is introduced is to emphasize the fact that this entire body has this angular velocity and this angular acceleration. So if I look at any point, I will have the same angular velocity and the same angular acceleration. I hope that's clear. So that's why हम particles के लिए theta dot और theta double dot use कर रहे होते थे, क्योंकि particles के वो change हो सकते थे अगर हम खाली particles को देख रहे थे। लेकिन जब मैं पूरी body को देख रही हूँ, then body के सारे points, be it P, Q, ये point, जो मर्जी point लेना है, all of them would have the same angular velocity and angular acceleration. Right, perfect. So with that, what I want to jump into is actually looking at the motion of a particular particle on the body, कि उसकी फिर जब हमने ये थीटा डॉट थीटा डबल डॉट दैट इज़ ओमेगा एंड अल्फा डिफाइन कर लिए हैं, तो देन कैन आई एक्चुअली फाइंड the sort of the absolute velocity and acceleration of a point P which lies somewhere here on the body. So notice for that कि I am now looking at the sort of the situation from above. Let's say ये इसी plane को अब मैं अगर ऊपर से देखूं, then I can see कि P, or I've arbitrarily chosen this point. Okay, I can choose any other point, which I will do just shortly. So if I choose this point P, it has a position vector r from our origin O. ठीक है, और origin जो है lies on our axis of rotation, right? So let me analyze this motion using the tools that we already know. That is, let's analyze this particle P ka motion, and the particle P belongs to the body, using polar coordinates. ठीक है, पहले polar coordinates से करते हैं. So you guys remember when we use polar coordinates, we have to define first of all our basis vectors. So basis vectors क्या हैं? Polar coordinates लिए तो हमें पता है ये क्या होगी direction. This would be my UR. और थीटा अगर let's say इधर से कहीं से define हो रहा हो यूं करके, then my U theta is this one. ऐसा ही है. So उससे then I hope you guys recall what and I'm gonna need your help for this. You guys remember कि you remember that मेरी याददाश्त इतनी अच्छी नहीं है. So velocity in polar coordinates of a particle used to be r dot in the UR direction plus r theta dot in the U theta direction. Right. So that I think that's, if I go wrong, please correct me. Or ab to I'm guaranteed to make a mistake. The acceleration used to be, पहले मैं UR वाला लिख लेती हूँ. कुछ ना कुछ उसमें R डबल डॉट तो ज़रूर आना था. अब आगे क्या था?
R theta dot square.
R theta dot squared. Let me look at my notes very quickly. I don't want to make a mistake here. So yes, it is. Very good. Good memory. So R double dot minus R theta dot squared in the UR direction, and in the U theta direction it used to be R theta double dot plus 2R dot theta dot. ठीक है, differentiating this part. बिल्कुल. Right, this is the velocity and acceleration of a particle which we've looked at before in polar coordinates. So now let's take a look at this particle P which is lying on the body. First of all, let's notice that because this body is a rigid body, उसका मतलब ये कि ये P का distance from O is not going to change. That is, there is going to be no change in the magnitude of R dot. R will remain unchanged in its magnitude. So फिर ये R dot तो ज़ीरो हो गया. उसी तरह जब R dot में कोई change नहीं है, तो there is no double differential of R, मतलब there is no rate of change of the rate of change of R. So even R double dot is zero. So now let's look at कि हमारी उसकी वजह, इन दो चीज़ों की वजह से, just because it's a rigid body, हमारी क्या क्या terms have disappeared. So clearly this is gone. What else is gone? R double dot is gone. And then what else is gone? 2R dot वाली term भी चली गई. So पीछे बचा क्या हमारे पास? First things first, I've got that my velocity is then R theta dot. Can I please just keep it, अब U theta direction में है, sure, as I've drawn right here, velocity की direction. But let me be even more sort of simplified even further, और just उसका scalar version देख लेते हैं कि velocity का magnitude क्या होगा. That's going to be R theta dot. Now remember कि for a body we represent this theta dot using what? क्योंकि सारी body का same है theta dot. That is actually what? Anyone?
Omega.
Omega, exactly right.
Omega.
It is its angular velocity omega. So I get that the velocity उसका magnitude is then just omega times r, और उसकी direction as I've drawn my r and theta is in the u theta direction. That is, it is just tangential to the path, as we all know velocity always will be. ठीक है जी. So velocity का we've figured out okay, what the expression is for the velocity of a particle p. Now let me just generalize this further just to note okay, the only thing that's changing as I go to some other point, let's say this one q right here, is the r, the value of the radius, the radial position changes. That's it. So q ki velocity will be different from p because its radius is different from the axis of rotation, whereas omega remains unchanged. और of course ये scalar की मैं बात कर रही थी, q के लिए अपने ही directions होंगी, that is it will again be having its own path और उसकी जो है कुछ tangential direction something like this होगी for q. Perfect. So we figured out the velocity for a particle. It's just, let me, velocity ka magnitude is just equal to omega times r. Now let's see what happened to the acceleration. Acceleration ke liye I'm going to keep my vector form. Why? Because there are actually still two components of it. So let's see. R direction mein I have minus r theta dot square. और u theta direction में है r theta double dot just remaining. Simplifying this, noting के theta dot is omega, और I hope कि someone can tell me what theta double dot is.
Alpha.
Alpha,
Yeah,
exactly.
alpha.
For the entire body, exactly right. So alpha then turns out to be what? Minus r omega squared in the ur direction plus what? Alpha r u theta. आमतौर पे ये याद करने के लिए ना, एज इन आई नो कि आप लोगों को याद नहीं करना, लेकिन यू सीन कि समटाइम्स इट्स यूजफुल टू जस्ट कमिट थिंग्स टू मेमोरी. तो इसको द ईजियर थिंग दैट पीपल टेंड टू मेमोराइज इज माइनस ओमेगा स्क्वायर्ड आर एंड अल्फा आर. दैट इज वी ब्रिंग द आर जस्ट, देयर इज़ नो, मतलब उसका कोई पर्पज़ नहीं है क्योंकि ये स्केलर्स है सब कुछ इस वक्त, लेकिन जस्ट फॉर यूजफुलनेस टू मेमोराइज इट. सो minus omega squared r in the ur direction plus alpha r in the u theta direction. That is, for the acceleration of the point P, we have two components. One component is, as we can see, in the minus ur direction. मतलब ये कि towards the center of curvature, towards O, and the magnitude of it is omega squared, excuse me, omega squared r. And then in the theta direction, this direction, we have a magnitude of acceleration which is alpha r. Great. So we have basically, and as I said before, okay, I was just using p as an example. Even for the acceleration, if I just consider q, तो उसमें फिर क्या हो रहा है? ओमेगा और अल्फा तो पूरी बॉडी का होता है. So the only thing that's changing here again is just the radius of the particle of the body. So this allows us essentially, हमने particle kinematics को use किए, but we've essentially applied it to the motion of each particle on the body, and we've seen that for all of them they have the same angular velocity and acceleration. Lekin when we find the absolute velocity and absolute acceleration, then we do have to take into account कि उनका what is their radial distance from the axis of rotation. Great. This thing is actually, I just use polar coordinates. So I just to show you guys कि हमें इसमें कुछ fancy चीज़ याद करने की ज़रूरत नहीं है. हमें पुरानी चीज़ों से ही हमारा rigid body rotation का analysis भी हो जाता है. But इसी को just to hone in on that, let me also use what's the word? The NT coordinates, normal and tangential coordinates. And let's see for those what happens. Now, first of all, वो velocity वाला we'll do that as well. So, for normal and tangential components, let's assume that it's rotating. It's given like so, right? Omega is rotating like this. So this would be our omega, and our alpha would also be in this direction. Then, I can see from just my direction of the curl that iski velocity is going to be in this direction. So of course velocity ki direction, that is my tangential direction, or normal direction is towards the center of curvature, where in this case the center of curvature is of course O. So then what do I have? I have that my velocity is, the vector is actually ds by dt in the tangential direction, या फिर as we used to just write it के the scalar velocity का magnitude in the tangential direction. और अभी polar वाले analysis से I've seen that that is actually omega r in the tangential direction. इसको थोड़ा सा let me not just assume कि मुझे polar की वजह से पता है. Let's also substitute के s तो is this curved path, right? So s के अंदर क्या है? s के अंदर होता है of course r theta का dt. So I think you guys are all capable enough कि if I want to differentiate this I have to use the product rule, but noting के product rule के अंदर r dot is 0, so I just have r times d theta by dt या फिर r times theta dot, that is I have omega r as before. So again I'm getting the same thing. और इसी तरह let's also write down the acceleration. You guys tell me. Acceleration is what? It's v dot in the tangential direction plus v squared divided by rho in the normal direction. Okay. So v dot के लिए I have my omega r का differential. Right? इस velocity के scalar का differential plus v square के अंदर भी let me just pop in के I have my omega r का squared divided by rho, which is in this case just r. So simplifying all of this, again noting के the differentials of r are all 0, r is not changing in length, so I just get what? Omega d omega by dt, so that's alpha times r in the tangential direction plus simplifying this, omega squared r in the un direction. Now comparing this, we can see that we're actually getting the same stuff back whether we consider this, the normal and tangential components, or we consider the polar coordinates. Importantly, the only difference being in this case with the normal and tangential is that the normal direction is reversed from the radial direction. इसलिए इस केस में यहाँ पे plus omega squared r आ रहा है, whereas in the other case we had alpha r in the u theta direction minus omega squared r in the u radial direction. और ये minus क्यों है? Again look, ये un is pointing towards the center of curvature, whereas if I had drawn my u theta and ut, तो मैंने u theta को तो इसी direction में draw किया था, but my u r was in the opposite direction. It was outwards, right? The radial direction is pointing out from the origin. So that's why there is just this difference in the minus. Everything else is basically the same. Importantly, ये हो क्यों रहा है सब कुछ? Because as we had noted in our polar, when we were doing polar coordinates and normal and tangential coordinates for our particles, हम लोगों ने note किया था कि they do coincide when we have circular paths. Why? Because r constant होता है उस केस में, इसी वजह से यही हो रहा है इधर भी. एक पार्टिकल p अगर मैं ले लूँ तो उसका r चेंज नहीं हो रहा, whereas if I take some other particle q, फिर उसका अपना r है लेकिन वो चेंज नहीं होता. Right, okay, so we've got all of our velocities and accelerations under the planar या फिर rotation of a body about one fixed axis. So let's jump to doing some examples of this. I want to just iterate that in the slides it's done in even more detail, but basically it's everything that we've discussed. But it's just worded in a slightly different way. So it'll help you consolidate everything that we just discussed regarding the velocity and acceleration of the different particles on the rigid body as it rotates about a fixed axis. Okay, so let me quickly read through the other way of doing it. So velocity ka we've done the same way, which is ke r theta coordinates ka kar le. But one more thing to point out is that I'd skip to just considering the magnitude of velocity kya hai. It's just omega r. But this velocity can also be represented in its vector form. Or vector form mein, I think it just suffices for us to note that it's actually just a cross product between the angular velocity and the radial vector position of our particle. So it's just omega crossed with r. Okay, now note of course कि cross product of vectors के अंदर the order is extremely important. So that's why we must remember that it is actually omega crossed with r. Okay, or either r actually can be any vector of that particle p from just this axis of rotation. So मतलब ये कि वो ये भी हो सकता है. This can be an RP, it could be this one, but they would all give us the same cross product. Now, you're welcome to think about it why that is. It's basically got to do with the fact that there's an RP sine phi that comes into the cross product basically, or वो RP sine phi जो है ना, that's always going to be this R जो ये वाला था, वो जो in plane का R था, it will always be this. Okay, so that's why it's just omega crossed with a radial position defined from the axis of rotation, from any point on the axis of rotation. Okay, and as I think you guys know from your vector calculus, the cross product ki direction is again given by our right hand grip rule. Perfect. Okay, so that's for the velocity. Just highlighting that these two are important, so it's good to note how they're coming about. And then for the acceleration, either we can use the analysis for the polar coordinates or the normal and tangential components, and just note ke wo cheezein hain kya, uske wo components honge kya, as we've done. So as we've discussed, the tangential component, this is this one, tangential components is actually alpha times r, whereas the normal component, this one, which is pointing towards the center of curvature, is omega squared r. And again, it's worth committing these to memory, although we will be provided this whenever we need them or we can look them up. Okay. Yes, of course. Physically, what these things mean are exactly the same as they meant when we were looking at the kinematics of a particle. That is, tangential component contains the rate of change of the magnitude of the velocity, whereas the normal component contains the rate of change of the direction of the velocity. And the normal component, of course, is always directed towards the center of curvature, which in this case is going to be towards the axis of rotation. Perfect. So we've got everything covered. Yes, ये scalar forms है, इनकी भी vector forms को consider कर लेते हैं. Now noting that we knew that the velocity in vector form was omega crossed with r. So iska, the acceleration is of course just the derivative of the velocity, it's the rate of change of velocity. So differentiating this and applying the product rule, जिसके अंदर product rule तो आप लोगों को याद ही होगा, u v का prime is equals to u prime v plus u v prime. So the same thing applies here, or वो cross product वैसा का वैसा आ जाता है. So applying the chain rule to this velocity, then we get these two terms. Or in those terms, let's start to point out what things we know. So I think we all know what d omega by dt is. That's alpha. We also, I think, know what dRp by dt is. This is the rate of change of the position in the vector form. So that is the velocity of the particle. So substituting those things, or velocity का हमें पता है it's omega crossed r. So substituting all of that back into acceleration, हमारे पास ये expression आ जाती है, which is the vector form of the acceleration, absolute acceleration of different points on the body. Their rp would be changing. That's it. Okay. इसी को मज़ीद simplify अगर करें तो I want to just point out कि alpha crossed rp का magnitude is just alpha times r being in the plane of the path, और उसकी direction जो है हमें पता है this is in the tangential direction. और इस वाले पूरी चीज़ की omega crossed with omega cross r again has the same magnitude that we've already discussed prior to this, which is omega squared r, और उसकी direction is in the normal direction like so. That is towards the center of curvature या फिर in the minus r direction. Okay, so उसी उन्हीं expressions को हम ये vector form में भी लिखते होते हैं, but just the point is कि even in the scalar form they're good enough for us because we ourselves define कि वो at और an की क्या directions हैं. तो if we just find the magnitudes of the directions, then we know overall कि वो vector क्या है. Okay, so just as we've noted कि at, the tangential acceleration is alpha times r in the tangential direction, and the normal component is omega squared r in the minus r direction, या फिर in the normal direction, or magnitude total acceleration ka as always with the vector analysis. Perfect. So that's it for our rotation about a fixed axis. Now let's actually jump into some examples. So just noting down a short summary of what we've done. Okay, we use the right hand grip rule to define the sign convention of our rotatory motion, ताकि हमें vector direction हमारे thumb की point से मिलेगी. Then we also saw कि for the rotatory sort of angular, rotation से related angular velocity, angular acceleration, they take these expressions which are very similar to our case for rectilinear motion, और इसीलिए उनके ऊपर हम constant acceleration अगर हो, then we can use those familiar expressions for our use जो हम पहले ही consider कर चुके हैं. And then when we're looking, this is of course the omega alpha are for d theta, the change in angular position, omega and alpha are the same for every point in the body. Doesn't matter how far or close it is because वो rotate कर रहे हैं ना सब. So rigid body ने जब all the particles are going to be rotating by the same amount and the same velocity and the same acceleration. Whereas जो उनकी absolute velocities हैं, they then have to be found using our expressions that we've just derived, where velocity is just omega times r, and for the acceleration we have two components, that is one in the tangential direction which is alpha r, and one in the normal direction which is omega squared r. Yes, and then vector quantities भी वही information हमें दे रही हैं, except when we do slightly more complicated problems, particularly when you guys move on to the mechanics of machines and whatnot, तो फिर vector form becomes extremely important in 3D. Even in 2D, when we go to general plane motion, we will see how the vector form is important for us to use. So for now though, we are looking at simple problems. We're just looking at rotation in a plane for which we can define our coordinates ourselves. We can define the basis directions ourselves. So हम scalar quantities को use करके we can get away with things. Okay, so any questions with what we've just introduced with the velocity and acceleration of the particles on a body which are rotating? Anyone? If it's clear, please acknowledge that it's clear.
Clear, ma'am.
Okay, thank you, Tala. So, pens, papers, calculators out, or let's jump into looking at an example. Now you remember कि हमने start ही इसलिए किया था कि for loads of engineering problems we have rotating parts, and hence we have to use rigid body analysis, and we have to use kinematics of a body. Or most often we also have our engineering parts are actually behaving like a rigid body. तो इधर यही एग्जांपल देखते हैं कि जी ये एक फ़ैन है, perhaps like an exhaust fan, which is of course being driven by a motor. So वो motor with a cable pulley system attached है, and then that drives the fan. So let's now do this analysis, as you can see, this is something which very commonly occurs in engineering problems. That some rotatory motion is being driven by a motor. So what's happening is that this motor, when it starts to begin its motion, it has a rotation with an angular velocity given like so. Okay, then of course ये e to the power minus t, I invite you guys, please try to draw कि ये omega की क्या profile आएगी, then it will make sense to you. I think it will look something like this. That is the point being कि starting में उसकी motion जो है वो variable होता है, and then afterwards उसका angular velocity जो है ना वो constant हो जाती है. That is, it goes into the case of zero angular acceleration. So अभी हम ये इस initial part में interested हैं कि इस वक्त क्या हो रहा है when the angular velocity is, it's revving up, it's increasing it. So now what we want to find is, okay, we want to find the magnitude of the velocity and acceleration of this point P जो fan blade पे कहीं दूर जाके है when the time is 0.5 seconds. ठीक है, perhaps you want to see के कितने 0.5 seconds के अंदर is the speed going to be enough to cause considerable damage to अगर कोई हाथ आ जाए या what not. There's so many other problems that could be involved when we want to analyze what is the motion of the particle P right here. Acha, now please note that the motor is being driven right here, and then using this pulley and cable system we drive this wheel on the fan. Now what's important to note is कि जो भी इस केबल का मोशन होगा वो constant होना है for the motor or for the fan. So it's cable driven, right? So let's see कि उसका क्या फिर मतलब है. तो मतलब ये कि अगर हम इस केबल का मोशन इस मोटर की वजह से फाइंड कर लें तो हमें उसकी वजह से पता है कि इस व्हील का क्या मोशन होगा. Although there is one extremely important assumption that we are going to be making here, which is that we're going to be assuming कि वो केबल slip नहीं करती off of the wheel. मतलब ये कि जो भी मोशन केबल का हो रहा है linear motion वही मोशन हो रहा है on that surface of the wheel right here, of the pulley right here, या फिर of the pulley right here. That is, the cable does not slip off of either of these pulleys. Okay, so let me just go through the plan of action that we're going to have. So first of all, of course, कि हम अगर इस मोटर की angular velocity को use करके इस केबल की velocity और acceleration को determine कर लें, then we know कि जो चीज़ इधर होगी वही केबल का velocity होगी right here, और acceleration का एक component which I'll discuss just shortly with you guys. And then once we know कि अगर वो cable इस तरह move करी, then that's going to cause the wheel to rotate with that same sort of tangential motion. So then we found essentially कि इस wheel की क्या rotation हो रही है. And then finally of course ये blades इसी wheel से attached हैं, so then we can use that angular motion to find what the absolute velocity of the point P would be. अच्छा, just one more thing to note कि I know कि the diagram has these values of the radii, लेकिन we've changed it up in the slides just to mix things up a little bit, और जो analysis slides में हुआ है that's being done for these radii. That is, the radius of this pulley of the motor is 1 centimeter instead of the 2 centimeters. And the fan ka pulley, ye wala, that's instead of 8 centimeters, that's going to be 4 centimeters. And this radius of the particle P away from the axis of the fan is 16 centimeters, not 32 centimeters. Okay, with that, so let's jump in. So सबसे पहले we know that omega is this one for the motor. ठीक. So why don't I just find what is going to be the angular velocity of this motor pulley at t is equals to 0.5 seconds. So that is omega at t is equals to 0.5. So substituting things in, I have 4 into 1 minus e minus 0.5, or that is going to be equal to what?
1.57.
1.57. Very good. And that is radians per second anticlockwise as it's drawn here. ठीक है जी. Perfect. Phir next, I think we all know now okay, alpha, the angular acceleration is what? That is d omega by dt. So just finding d omega by dt, ये expression है हमारे पास. अब ये थोड़ा सा एक्सपोनेंट की अंदर की मुझे भी थोड़ा सा भूल रहा है, लेकिन आई थिंक इट वुड जस्ट बी 4e माइनस टी, क्योंकि वो माइनस माइनस से मल्टीप्लाई हो जाएगा और t का डिफरेंशियल इज जस्ट -1. सो दैट्स व्हाट द angular acceleration is. Now of course, what is the angular acceleration at the time that we are interested in? Anyone? Oh,
2.43.
perfect. Radian units क्या होंगी?
Radian per second square.
Radius per
Perfect, thank you. Radian per second squares. Again, also anti-clockwise. ठीक है जी. So because it's positive, that's why it's still anti-clockwise. Right. So if we found omega and alpha, now let's come to it कि इस पुली को अगर हम देख रहे हैं तो वो जो केबल है वो उसकी बिल्कुल सरफेस पे जाके टच होती है. मतलब ये कि if I want to find the velocity and acceleration of the cable, then I have to use the radius of the pulley because वो केबल जाके सरफेस वाले पार्टिकल से चिपकी हुई है या टच हो रही है इधर. Right? So that's why the velocity of the cable as it goes, as it rotates over because of this pulley is going to be omega times r being 1 centimeter. Does that make sense? So we get of course यही चीज़ into this, so 0.0157 meter per second this time. The velocity of the cable as it is moving or rotating because of the motor pulley. Perfect. Secondly, now let's also notice कि उसकी acceleration क्या होगी. Now this is something important which I want to discuss, which is that of course the acceleration has two parts, right? It has the tangential and the normal components for the acceleration. Now remember that these two components mean different things physically. The normal component just represents the rate of change of the direction. अब क्लियरली वो पुली जब यहाँ से जो केबल जब यहाँ से रोटेट करेगी कि उसका डिफरेंट रेट ऑफ चेंज ऑफ डायरेक्शन है, वेयर जब वो यहाँ से रोटेट कर रही है उसका एक डिफरेंट रेट ऑफ चेंज ऑफ डायरेक्शन है. और ऑल्सो प्लीज़ नोटिस के मतलब उनका मैग्नीट्यूड तो बेशक सेम होगा, वो डायरेक्शंस हर डिफरेंट पॉइंट पे डिफरेंट होगी ऑन द आउटर सरफेस ऑफ द व्हील ऑफ द ए एन. बट वेयर इज इंस्टेड ये जो ए टी है एक्चुअली उसकी डायरेक्शन से कोई फ़र्क नहीं पड़ता, बट एनी वे सॉरी फॉर दिस, जस्ट फोकस ऑन दिस पार्ट कि जो ए टी है, the tangential component of the acceleration, that is the one that's representing the rate of change of the magnitude of the velocity. That is कि जो यहाँ से उसका sort of जिस मतलब v डॉट जो भी बन रहा है उसको ये represent कर रहा है. और अब ये v डॉट जो है ना वो केबल का जैसे वो यहाँ से मूव करेगी फिर वो थ्रू आउट उसका because of this, because of it being driven, this rate of change of the magnitude will be the same. So that is कि it's actually the tangential part of the acceleration of the cable which remains unchanged whether it moves here or here or here. क्योंकि उस पूरी की पूरी ने सेम वेलोसिटी और सेम रेट ऑफ चेंज ऑफ द मैग्नीट्यूड ऑफ दैट वेलोसिटी से रोटेट करना है. सो माई पॉइंट बीइंग कि अभी जो ये हम वेलोसिटी और एक्सेलरेशन निकाल रहे हैं इसमें ऑल दैट वी आर इंटरेस्टेड इन एक्चुअली इज द वेलोसिटी ऑफ द केबल एंड इट्स टेंजेंशियल एक्सेलरेशन. दैट्स इट. बिकॉज यही दोनों हैं जो उसके थ्रू आउट सेम रहेंगे magnitude mein. They will stay the same in the magnitude. So that's why let's just find the tangential component, or someone nice and kind will now remind me what is the tangential component. Chale, abhi it's a little fresh, so I'll go ahead with this. I should have written it down. I'm sorry I've missed it out. So I'll pop it right here. V is equals to omega r. A tangential is equals to alpha r. And A normal is equals to omega squared r. So A tangential is alpha r. So that is ye alpha ye raha. R is 1 to the power minus 2. So that's just
0.02.
0.0243. I'm keeping it to 3 significant figures. Meter per second squared. Perfect. और अब यही वेलोसिटी और एक्सेलरेशन जो है एज आई सेड वो केबल की सेम रहेगी, द वेलोसिटी एंड द टेंजेंशियल कंपोनेंट ऑफ द एक्सेलरेशन. So even when it goes around the big wheel of the fan, this velocity and acceleration remains the same. But the only thing that ends up happening now as it goes over here is that we have the angular velocity of the fan and the radius जो भी यहाँ से यहाँ तक है जो क्या था हमने 4 सेंटीमीटर है. Any question? Please keep an eye on your mics. Oh, sorry. Thank you. So this then tells us what omega f is going to be. That is the angular velocity of the fan, the entire fan. And that turns out to be 0.393 radians per second. That is, please notice how interesting this is. हमने omega of the motor was, मैं इधर ही कहीं लिख देती हूँ, 0.1 नहीं क्या था 1.57 था, sorry, yeah 1.57. So by changing the radius of the pulley of the motor and the fan, we've changed के क्या angular velocity we get of the fan. .43. Okay. Similarly, the A tangential remains unchanged. So that is also going to be this one right here. So that is equal to 0.0243. So alpha, the angular acceleration of the fan, then turns out to be 6.075 radian per second squared. Oh, made a mistake. Apologies. कुछ गड़बड़ लग रही थी. I was thinking ज़्यादा कैसे हो गया? SX8. Perfect. And now that we know the sort of the what is the angular motion of the fan, फिर हम ये point P की absolute velocities and accelerations निकाल सकते हैं, because of course this point P on the fan is rotating with the same angular velocity and angular acceleration as the fan. So then our velocity of the point P becomes omega fan times the radius of at P. So that is, मैंने आपको कहा था कि हमने change कर दिया. This is 16, this was 4. So that is just 0.393. Could someone just tell me what it is, having found it beforehand? Where is everybody? Okay, I'll ask specific people. किसकी शामत लाएं? Abdul Rahman. Tala, can you not hear me?
Yes, ma'am, I can hear.
आवाज आ रही है?
फिर ये कोई जवाब क्यों नहीं मुझे मिल रहे?
Ma'am, AT 0.097 है.
Thank you. और AN? In case someone does not remember, AT was alpha R and AN is omega squared R.
0.025.
Perfect. So the magnitude of these two turns out to be about 0.1 meter per second squared. ठीक है जी. So please do confirm if there's anything mistake.
Yes,
Any.
ma'am.
ठीक है जी. Thank you.
Yeah.
So we have essentially transferred motion from the motor onto the fan, and using the अभी हमने rotation about one axis, about one fixed axis, that is rotation within one plane का analysis use करके we managed to find the velocity of the position, velocity and acceleration of the particle P right here on the fan blade. Note one main assumption that we'd made कि that cable जो है it does not slip over the pulley, और उसका फिर और neither is it's also a rigid body basically. The cable itself also is a rigid body. It does not extend, वो stretch नहीं हो सकती. तो उसकी वजह से ही हम उसकी velocity और फिर जो भी मतलब जो भी चीज़ उसकी tangential direction में है ना उसका magnitude same रहता है. That is कि उसकी velocity and its tangential acceleration remain constant no matter where we look at it. इधर से इधर से इधर से इधर से and so on. And that's why हम ये केबल के velocity और acceleration को use करके इस fan के motion को analyze कर सकते हैं. Right. So it is 12:55. There was just one more example that I wanted to discuss with you guys. But I guess we'll pick it up next time. We'll pick it up next time. And again, this is an example of a motor being used to drive a lifting mechanism. Okay, Chale, so I'll end right here. If you guys have any questions with our previous example of the exhaust fan, do ask me. I'm still around. Otherwise, you guys are welcome to go. Or thodi, please come on, be a bit more engaged, right? Okay. Take care, ji. Allah Hafiz.
Allah Hafiz, ma'am. Allah
Allah
Hafiz.
Hafiz.
Ma'am.
Ji.
Excuse me, ma'am.
हाँ जी.
Ma'am, it's a bit out
Ma'am,
of
last
context, but
observation of
Could the person who is saying it's a bit out of context go first and then the other one?
yes, ma'am. What if the diameter of the circular disc or something, the cable over which the cable is bound, at the motor side is larger? Would the acceleration then the transfer would be greater than?
Yes. So you are asking ke what if कहीं मैंने इसको यहाँ पे मैं what if this motor wheel is larger, that is the driving wheel is
Yes.
larger and the other one is smaller, then you're exactly right कि फिर इसकी angular velocity कम होगी और ये ज़्यादा तेज़ी से rotate करेगा. This would have a higher angular
Why don't we
velocity.
use it in real life applications then?
I am pretty sure we
Actually,
do use
motor
it.
छोटी
No,
होती
no,
है.
no, we do use it, but in some other directions. So, kabhi kabhi, let me think of that example. Ke when would we be doing it? I'm thinking. अच्छा, this
The cycle.
एक मैं आपको बताऊं. नहीं, cycle में भी you have a smaller wheel driving the larger one. हम छोटे वाले को rotate कर रहे होते हैं और फिर वो बड़ा वाला.
But the chair is on a larger diameter
Oh, that's
disc.
true. That's true. Good point. अच्छा, just to note कि this is not really a matter of कि इससे कुछ नुकसान हो रहा है या फ़ायदा हो रहा है, because वो losses are independent of this. It's just a matter of कि हम क्या velocity या rotation provide कर सकते हैं और हमें उससे वापस क्या चीज़ चाहिए. ठीक, एक बात. दूसरी ये कि आम तौर पे मोटर्स जो है ना वो इतनी सारी डिफरेंट वैराइटीज़ में आती हैं कि अगर आपको तेज़ भी वेलोसिटी चाहिए ना, एंगुलर वेलोसिटी, यू वांट अ फास्टर रोटेशन, यू कैन एक्चुअली जस्ट बाय ए मोटर जो आपको वो अलाउ कर रही है. लेकिन लेट्स से कि आपके पास ऑलरेडी एक कलेक्शन ऑफ मोटर्स अवेलेबल है और उसके अंदर आपके पास ये एक ही थी, मेरे पास है, मैंने वो यूज़ करनी है, मैं नया नहीं ख़रीदना चाह रही, तो फिर वी कैन यूज़ ए सॉर्ट ऑफ have a smaller driven wheel या driven gear and change it up. That's completely up to us.
Thank you, ma'am.
ठीक है जी.